Hi, I'm Matt Godbolt and I would like to talk to you about my Sega Master System emulator. This is the first emulator I wrote in JavaScript. I also have a BBC Micro emulator which is a lot more advanced, and there's already a talk about that, but I'd like to talk today about this Master System emulator. So first of all, why would you emulate a Master System? Some of you may not even know what a Sega Master System is. It was an 8-bit console back in the 80s, made by Sega and had many of their popular games. But the real reason I chose to emulate the Sega Master System is that it was my first console, and I remember vividly going to France on the ferry, and on the ferry there was an Altered Beast coin-op, and I played it with my sister and we had a great time, and I thought it looked amazing, and I saw the graphics and I thought I'd love to do this at home. I'd love to play this game at home. And I saw that there was a Sega Master System version, and I saved up some pennies and eventually was able to buy a Sega Master System. I unwrapped it and we put Altered Beast in and we played it, and unfortunately back in those days the graphics weren't the same as the ones we saw in the coin-ops, so we were a little bit disappointed, but nonetheless it was my first console and I love it very much, and my favourite ever game is actually on this console. I loved it so much, in fact, that with my good friend Richard, or rather Richard sort of started it and then I picked it up with him towards the end, we wrote a Sega Master System emulator so we could play our favourite Sega Master System games for the RISC PC, or the Archimedes. And here is a screenshot of me about to run Miracle, which was the name of our emulator for the Sega Master System. I did try to get my RISC PC emulator up to scratch enough to be able to run the Sega Master System emulator we wrote on it, but I was unable to. But you'll have to trust me that we were actually able to play and run Sega Master System games on our Acorn Archimedes and RISC PCs in the mid to late 90s. This was, of course, the first version of the emulator, and I owe a huge amount of debt of thanks to Richard Watkins and the other people that we found along the way to help us understand how a Sega Master System works. So what's inside one of these things? Inside is an 8-bit Z80 CPU. It has 8 kilobytes of RAM, which is not very much at all by today's standards. It has a custom video processor, the VDP, the Video Display Processor. On that processor there was a 16K of RAM that was just accessible by that processor directly, at least. It generated a 256 by 192 64 color output, which is absolutely minuscule by today's standards, although it was scaled up obviously to fill the whole screen. It had a fairly standard SN76489 sound chip, and the way that you plugged your games in was to slot in these cartridges. So here you can see this Double Dragon on the right hand side. That is one of the ROM cartridges that you would plug into the top. There was also a little port on the front where smaller ROMs could be just slid in like credit card sized, and that Teddy Boy Sega card image there shows you what one of those looked like. Those ROMs would have anywhere between 32 to 256 kilobytes of ROM. So an 8-bit machine typically has a 16-bit address space. 8 bits would obviously not be quite enough to write anything meaningful with. So the Z80 or Z80 sees 64K of address space at any one time, and it's broadly broken down into 4 slices. Starting from the top, we have the 8K of onboard RAM. Let me see if I can get my mouse pointer to work. Yes, so the very first top slice here between C000 and the top of RAM, the top of the address space, is 8 kilobytes of the onboard RAM split up twice. There's a mirror at the top, so you actually get to see the same 8K twice, which is just a weird oddity. They just didn't wire the top pin in, presumably, to the RAM controller, or they were thinking of supporting 16K to start with and then didn't towards the end. There is something magical about the very top 4 addresses, but we'll talk about those in a second. But essentially this is 2 banks of identical 8K RAM, and mirrors I should say. There is exactly only 8K of RAM, you just see it twice. Then between 8000 and C1000 hex, there is some page of the ROM that has been slotted in. If you recall that the ROMs could be as big as 256K or even perhaps even bigger, the way that you would be able to access different aspects of the ROM would be to program in which slice of ROM appeared at this location. And so you could change that here. You could page in and out the ROM, or indeed RAM at that location. Some of the cartridges would have their own RAM on them as well. Some of the more things like Phantasy Star, which had a lot more stuff going on, required a bit more RAM too. And so they placed some RAM on the cartridge and were able to access the RAM there. Then between 4000 and 8000 there's another page of ROM, and then between 0 and 4000 yet another page. So we have these 3 selectable pages of ROM. We can pick 3 16K slices of the ROM and pick and choose which ones we want. This gives us sort of 48K of ROM that we can see at any one time. Let's talk a little bit about this blue section at the bottom. Between 0 and 400 in hex, there is 1 kilobyte of ROM that always comes from the 0th bank of ROM. It's always bank 0. And that's because the processor requires the things like the interrupt handlers, the reset handlers, NMI handlers to all live at this particular address. And for convenience sake, that meant that you could place them in the bank 0 of your application or of your game. And then it doesn't matter which ROM page you selected for the remainder of that 0th bank at the bottom between 0 and 4000, you know that the interrupt handler and the NMI handler would always come from bank 0. You wouldn't have to duplicate that between all of your pages of ROM that you would like to page in. If that wasn't the case, you would have to put interrupt handling code at any bank of ROM that you'd like to page in at this bottom block here, which would be very inconvenient. So how do we page these things? Now we're going to go up to this area up here. We have these 4 magic addresses that if you write to, change what the memory layout looks like. So if you write a byte to FFFF, then you're selecting what the second page will be. And I've put RAM here, but it's RAM or ROM here. Likewise, FFFE and FFFD select the 0, 1 or 2, these 3 blocks here. They choose which slice of the ROM appears there, and then in FFFC you can configure whether or not the cartridge RAM or ROM appears at that bottom, this between 8000 and C1000 here. Again, that was only supported for some ROMs that had RAM on them, which is confusing. So I should say one of the cartridges that had both RAM and ROM in it. So if we're going to write a function in JavaScript to pretend to be the memory system of a Sega Master System, we might write something that looks like this. We're going to read a byte from a particular address, and we'll get to how we understand what the address is and when this is called in a minute. Effectively, we're just writing a bunch of if statements. If the address is less than that 400 hex, then we know that that's the very special thing that always reads from ROM bank 0. So we can have an array. We can have an array of banks of ROM, and the 0th one will always be accessed when we access hex 400. Otherwise, if it's less than 4000, then we know that we're just going to look up the page register and get the 0th page register out. That will tell us which ROM bank is currently mapped at the bottom ROM slot. We'll access that particular ROM bank, and then we'll say, well, let's get the byte from within that selected ROM bank. If it's less than 8000, then we're going to do the same, but we're going to do page 1. And of course, now the index into that page is going to be 4000 less than the address that we're given in. Otherwise, we'll be reading off the end of the first one, and so on. And then if we look at these other pages here, you can see that there's some more complexity. If we're going to look at the 8000 to C1000 block, there's some handling of whether it's ROM or RAM, which I've not put on here. Otherwise, we know we've hit the RAM, and if we've hit the RAM, we're just going to look at the RAM block given by the offset from the beginning of RAM. And again, then if we've fallen off the end of that part there, we know that we're at the duplicate of RAM So we're going to see the same 8K again, and this last line here covers that case where we're reading from E000 onwards, and we see the same RAM that we would have seen earlier, just repeated. So that's pretty straightforward, and you can see perhaps how we're going to start to put this together to make an emulator. Let's talk a little bit about the Z80 itself. I've got into the habit of saying Z80, I should say Z80. Obviously, natively I'd say Z80, but at work I've given up arguing about whether it's pronounced Z or Z, and so it's going to be Z80, Z80, whatever. So the Z80 itself. So this is the processor that's powering the whole show. It is a CISC chip, I don't think anyone could argue with that. It has 900 or more instructions with no multiply or divide. Interestingly, it has a separate input-output bus. Many of its contemporaries that I'm much more familiar with, for example the 6502, did not have a separate input-output system. In fact, they relied on magic memory areas to configure and talk to peripherals, but the Z80 wanted to have a separate channel for talking to those devices. So there are specialized instructions to input and output bytes onto like an I/O bus. That's how we talk to the sound chip, that's how we talk to the display chip, and some of the other peripherals on the system. It ran around about 3.53 megahertz. It depended on whether or not you were in PAL or NTSC regions, and the specifics of that are beyond my comprehension fully, but I think it was to do with saving the number of oscillators that they needed to actually have on the boards. It was not pipelined, and the minimum number of cycles it would take to execute a single instruction would be 4. So 4 cycles to do even the simplest thing, like a NOP even. So that's about a microsecond. So it's pretty slow. For a load or an add, you're talking more like 7 cycles. So again, the throughput is not very big, not very high, I should say. But it had an awful lot of cool features, which we'll get to on the other side here. So we have many registers, whereas its contemporary, the 6502, had 3 registers. Charitably 4 if you consider the stack pointer to be a register. The Z80 has 18 of them, and it has A through E, and then H and L, and then these sort of secondary A prime, B prime registers, which weren't directly accessible but could be switched in and out for their namesakes, and indeed the entire set of registers could be switched backwards and forwards, which is quite convenient. Obviously, it has flag registers for comparisons, it has interrupt handlers, it has the R register, which for the longest time I thought was a random number generator, but actually is the refresh for the dynamic RAM register. It tells the RAM system which bank of dynamic RAM is going to be refreshed next. And so, although if you were to sample it at sort of irregular intervals, you would effectively get a random number, it was also possible to write to this register, which means you could actually completely break the dynamic RAM by, for example, sitting in a tight loop storing 0 to the R register. But let's not worry about that right now. That's not very important, but it's just interesting to note that this was available to the programmer. These registers were also pairable to do 16-bit operations, and this is where the Z80 really shines. The AF registers were not particularly useful. This was the accumulator and the flags register, but you could push and pop it. But once you started looking at BC, DE, and HL, you have actually useful 16-bit operations that you can do. You could add HL to DE, and you could read using HL as like an index register. So this kind of took the place of the 0 page of a 6502. There are also 4 16-bit registers, that is explicitly 16-bit registers, some index registers called IX and IY, and then the stack pointer and the program counter were full 16-bit registers too. So let's have a look at what some Z80 code might look like. Here is just some fairly random opcodes here. On the far left-hand side is the address that we're disassembling. The second column in blue, I forget I've got a mouse pointer, I can point at these things. These here, the 212806, for example, that is the instruction encoding of the instruction we're seeing on the right-hand side here. So this is a load instruction, a load HL. So this loads the register pair HL with 2A06, except that because this is a little endian computer, the number actually loaded is 062A. This tells us, in fact, this is where the HL register gets its name from. The H is the high part and the L is the low part. So we're loading the high part and then the low part separately. Although that's not actually true, is it? Because that's 062A over there. So scratch that. I've obviously got that wrong. I thought that was the order that they were stored in memory, but perhaps the instruction encoding is different. Just goes to show, I don't know. Anyway, we can see that there's an operation here that's loading HL with 2A06 or 062A. The next instruction here is an add, and this is an add A with A instruction. So that's a single byte and effectively doubles the A register, the accumulator. So that's an 8-bit register being doubled. It's the same as shifting it up by 1. That would still take 4 cycles, even though it's a single byte here. Some transfers and other bits and pieces going on here. Here's a 16-bit add, for example, the 591 address. This 19 over here is the encoding for add HL with DE. So it's a pretty compact representation of the instructions. And in fact, all of these remaining instructions here are a single byte, even though some of them are pretty complicated. And I used to know what this routine was actually doing, but for the life of me, I can't recall now. So we'll just have to gloss it over. I've put some comments on the right-hand side here as to what each one is doing. And you can see that there's some very clever things going on, and I can't even remember. I think it's some kind of index table lookup now I think about it. Anyway, it's not really important right now. You can just see that there is a correspondence between the sequence of bytes in memory and how they're interpreted as instructions. And this is how we're going to build up our emulator of the processor itself. So how do we decode that sequence of bytes? Well, the Z80 has an optional prefix, which I don't think was shown on the previous slide. No, there are no prefixes in this. That's not very useful. These prefix bytes here change the meaning of the following instruction. So we've got some examples down the bottom. So we've got this optional prefix followed by a byte that explains what the opcode is doing. And then depending on what that opcode is, there's either 0, 1, or 2 following bytes that encode the operand. So here are some examples. The exclusive ORing A with A, which is a very common way of setting A to 0, is a single byte instruction of AF. That is, of course, less bytes than the equivalent of loading A with 0, and we can see what that would look like by looking at the next line. So this is loading A with the immediate value FF, 255. This would be 3EFF. So if we wanted to load A with 0 using load A, it would be 3E00, and it would take 2 bytes to encode that instruction. Instead, we can exclusive OR it with itself, and it only takes 1 byte AF. Down here, we're loading B with the context of an index register plus 15. This is one of those examples where there is a prefix byte. This prefix byte DD says, in the following instruction, any references to HL should be interpreted as being IX. So if we were to just look at 460F, that would be load B with HL plus OF. But instead, this DD means use the index register in place of HL. So DD46OF is load B with the index, the memory address pointed to by the index register plus 15. That's kind of a powerful thing to be able to do in a single instruction. And you can see that this OF here corresponds to the constant offset that's been placed in the instruction. And then finally, this ED opcode over here. For the life of me, I can't recall quite why this is needs an extension. But obviously, it shifts the instruction in some way from some other point. Apologies for not being able to remember it off the cuff. I thought I remembered all of these things, but clearly not. It's been a while. So what would our JavaScript look like? Well, the main loop would say, fetch the byte that's currently pointed to by the Z80's program counter. And we might as well automatically increment that too. That's this z80.pc++. And our read byte function is the function we've already seen, the one before with all of the cascading ifs to determine what actual piece of either ROM or RAM we should read from. And then we have a huge switch statement. And for every single opcode, we just write the implementation. So, for example, that AF, if you recall, was an exclusive OR A with A. So let's do it. Let's do z80.a exclusive OR z80.a, assuming that this Z80 structure has all of the registers sort of written out inside of it. And then we're done. We've already incremented the program counter. We're going to break out of this, and presumably we're going to stay in a loop executing more instructions until we reach some terminating condition. Here is an example, for example, of an instruction that needs a constant that's in stream. So that 3e, if you remember, that was the load A with an immediate value. So here instead we're just going to do read A by reading the next byte pointed to by the program counter. So that will read the constant value that was after the 3e. So if you recall, we saw 3eff before to mean make A equal to ff. We would read the 3e, come down here. We would notice that we need to do another byte read. We'd increment the program counter again to read the byte, and then we'd set that in A. So there's 900 instructions, and there's the shifts to worry about as well, but effectively you just sort of plug your headphones on and you start plugging away at all of these. But it's really not quite that easy. We're missing out a few things here. When we load values into registers, a whole bunch of other things happen too. For example, there are a number of flags. Flags like the value you loaded was 0, or if you add values together, did it overflow? Did it carry? The Z80 has this notion of parity and half carries, where for things like binary coded decimal, if there was a carry from bit 3 to bit 4, then the flag would be set telling you that that had happened. The parity flag was always set to say whether or not the current byte was either even or odd. And of course then there's a sign bit that says the value that you loaded in was negative. So there's a lot of things going on there. So if we go back a slide and we look at this exclusive OR that we're doing over here with the A exclusive OR Z80.A, we'd have to set the 0 flag, because now the A register is 0. We'd have to clear the negative flag. We'd have to clear the carry flag and a bunch of other things like that. So it's not quite as simple as we've written out here. We also have to handle things like interrupts. If we were to just sit in a tight loop executing instruction after instruction after instruction, there would be no way for the simulation to end. I mean, you could do tens of thousands of them and then whatever, but we also know that some of the peripherals that are on the system are capable of generating interrupts. For example, the video blank signal. So when the beginning of a video frame happens, then the video chip generates an interrupt to say, hey, it's the start of a new frame. The Z80's interrupt pin goes low, and it's up to the CPU to stop executing where it is and to head off to some other part of memory by reading from that low area of memory, if you remember, the one that always comes from ROM bank 0. So we need to handle those in some way. There are also undocumented opcodes. Not all of the 256 possible instructions, or the however many more, 1024 if you include the 4 prefix bytes, had documented meanings, but they did things. The 6502 has a simpler design, and its undocumented opcodes are very well understood. I'm not really sure what the Z80 does when undocumented opcodes come along. So, I mean, I don't think many, or if any, of the commercially available games used anything that was undocumented, but it's something you need to think about. So, in summary, it was really complicated. It's complex to emulate a Z80. And so when I was writing this project, I borrowed an existing Z80 implementation from a JavaScript version of a Spectrum emulator, which itself was based on a C implementation of a Z80 processor. So big thanks to the JS Specky people for making their code open source. So the result of adding A, if we were to look at the add A, some kind of constant instruction, this is what actually gets generated. It's an awful lot more than our naive implementation that I showed you a moment ago. Some of these things are constant tables that are just set up once. But if we start from this var c equals read byte here, this is us reading the value that we're going to write, the value that we are going to add onto the accumulator. We calculate the result, so this is just a simple add. And now we need to do something very complicated, looking at the overflow bits from before, looking at the overflow bits afterwards, both the top bit and the half bit, and we generate together whether the top bits are set, and we kind of come up with a table index which looks into this SZ and HC and overflow tables, each of which has something which tells us what's going to happen to the carry, to the half carry, to the overflow, and then finally we look up the actual value, the final value, based on its result. So this sets the sign and the 0 and some of the bits that aren't defined inside the flags register. So obviously in the the SZ53, which is the sign and 0 table, half of those values with all of them with the top bit set will have the sign bit set. The value that's exactly 0 will have the 0 bit set, and so on. So that allows us to kind of reasonably quickly assemble all these complicated flags in one go. So we worked out what the new value of the A register was as a result of the add, and then we worked out what the resultant flags would be. And then we took 7 cycles. It's important for us to know how long that instruction took so that we can account for time later on, which with interrupts and other things is very important. So there were about 900 different instructions, as we said before. We already have a table of what opcode to like a human readable form. For example, 0 is a NOP, 1 here is load BC with NNNN, which means a 16-bit constant, a 2-byte constant. 02 is load BC, A. And the clever thing that both Specky and JSpecky do is that they pre-process this big table of values of ASCII effectively into JavaScript. And that avoids an awful lot of repetitive code. So again, there's 900 odd instructions. There's like 1,000 lines of Perl that generates 5,400 lines of JavaScript. So it will look at, for example, LDBC, comma. It knows that the case 1 will be set BC to NNNN, and from that it infers that it needs to read 2 more bytes, and then it places it in BC. So you write the generator code once, run it on this big test set of opcode tables, this sort of disassembly table, and Bob's your uncle, you end up with a huge amount of automatically written JavaScript, which is a lot easier than writing it all by hand, and a lot less error prone. If you can imagine, there's going to be a load BC, A, there's going to be a load DE, A, there's going to be a load HL, A, and they're all going to be scattered through the table. And having written it once and tested it for BC, it's going to work for DE, it's going to work for HL. So that's all I'm going to talk about for execution. Let's talk about something that's a lot prettier, the video display. So here we can see a beautiful output of, I can't think what it's called now, Fantasy Zone. Hugely very colourful, lots of sprites on the screen, a lot going on, almost impossible to see what you would crash into and what would shoot at you and whatever, but that's not neither here nor there. So let's talk about the VDP. As I said before, it has 16K of RAM just to itself. This RAM is on the VDP chip and is not part of the memory space of the Z80. The Z80 can't see that memory directly. It's only accessible by using the input and output pins and the input and output instructions that the Z80 has. That 16K of RAM contains a whole bunch of sort of sprite tiles and some palettes and then tables that tell it how to assemble those tiles to make both the background and the foreground sprites. It also has an interrupt generator which will generate interrupts at the top of screen and at various places down the screen if programmed. So what are tiles? Tiles are these 8x8 4-bit per pixel pictures that have one of 2 palettes. This is just a dump of one of the games. I can't even remember what it is. I think this is Wonder Boy 3. Yeah, I think this is Wonder Boy 3. It has a lot of data all over it. I think down here, this sort of bit here, which I always thought this looks like ET. This is what happens if you count upwards and you sort of interpret it as colours and pixels. I think this is probably the sprite table in the middle of it all, and then the rest of it is just sprite data itself. The tiles are so-called planar mapped. So each pixel can have one of 16 values. It's 4-bit per pixel. And so, for example, we might have the pixel values here. There are 8 pixels here, 8, 0, 0, 0, 0, 0, 15. And naively, you might imagine storing them as 8000015, or at the very least, combining this 4-bit value with the next 4-bit value to make 1 byte here between the 8 and the 0, and then another byte here, and then another byte here, and then finally another byte here of 0 and then 15, or 0f in hex. But just because hardware is funny, it turns out to be easier for the hardware if these are stored with the bits separated out. So we have 4 bytes in a row, same amount of storage. This first 8 value here needs to be represented in byte 0 as the 0, byte 2 as 0, byte 3 as 0, and then byte 4 as 1. So this is the binary representation of 8, 1, 2, 4, 8, but separated across 4 consecutive bytes. Similarly, the 0 here is zeros, and so are all the other ones. And then finally, this 15 here is separated again across 4 consecutive bytes as 1111 in the 0-bit position of 4 consecutive bytes. Each tile is 8 by 8, which means that we have 8 lots of 4 bytes, which is 32 bytes for each tile. The background itself is made out of a 32 by 24 arrangement of those tiles. So if you think about that each of those tiles is like a mosaic piece, we can pick them up and choose them as we see fit in a 32 by 24 array, and that's what the video display unit will show as the background. Each tile in that background has 2 bytes. We can have up to 512 tiles to choose from, so we need 9 bits to select which tile we would like to show at this particular location. The hardware supports flipping the tile in both the vertical and the horizontal direction, so we have 2 bits to control that, so we can have it vertically flipped, horizontally flipped, both or neither. We can pick one of 2 palettes, so 1 bit says either the base palette or the sprite palette. There's 1 bit that determines whether or not this background tile shows in front of sprites or whether it's behind the sprites. So typically, as a background, you would have it behind, but if you want to have like columns that your main character can walk behind, you would set that bit to say this tile shows in front of the of all the sprites. And then there are 3 user bits, which is kind of, they were uninterpreted by the hardware. They were used sometimes by games to store extra metadata about the tiles that you landed on, but ultimately they were just because there was no other way, there's nothing else to do with these bits, they were just left over. So that's the background. So here is Wonder Boy 3 in all of its beautiful glory, and you can see that this is, I've removed all of the sprites, we're just looking now at the background tile. So the background in this instance will also contain the top 2 rows here, which contain the status row, including the 1 heart I've got, the 1 potion I've got, and the 4 gold I've managed to collect so far. So those are all part of the background. Here is the first few lines of just the sprite number, the tile number table. I've highlighted areas that are interesting. So here, this 20 and this 20 here is hex 32. That's a blank. That's actually off the edge of the screen. You can't see that. But here, the 0212 and the 0313 encode for the tiles, the 4 8x8 tiles that make up the top left of the heart, the top right of the heart, the bottom left of the heart, and the bottom right of the heart. These hex 202020 appear to be these grey blank tiles. And then we get over to the potion bottle here, and this potion bottle corresponds to this 0616, 0717, again of the top left, top right, bottom left and bottom right of the potion. Now there's no number above, so there's a little blank space here. So that's also the hex 20, which coincidentally is a space in ASCII. And then if we look at the 01 underneath, we see 3031, which is in decimal 48 and 49, which is actually the ASCII codes of 0 and 1. It seems like the programmers chose, just to make things convenient, to place the text glyphs in the location corresponding to their ASCII code. There's no need for them to have been done that way, but that is how it's been done. And indeed, we see that pattern repeating up here with the GOLD of gold and the number 4 here. So that's kind of interesting. And in fact, if we go back to the sprite table, here, this is the 48, 49, 50 table. And you can see like the A, B, C, D, E, G. It looks like they've used, these are the only characters that are needed in the game, and they've left them in the right place, although that seems the pause is not in the right spot at all. How interesting. Well, anyway, we'll stop like picking apart a 25-year-old game. And we'll carry on looking. And the last thing here is just looking at how these clouds are put together. I haven't got enough room to show the whole screen, but you can see that the cloud is made out of a lot of tiles, 6A, 7A, or this kind of thing here, which is repeated in these 3 different locations to give us 3 different cloud areas here. So that's an example of the background. Let's talk about the sprites. That's where the interesting stuff happens. The hardware supports 64 sprites, which can be either 8 by 8 pixels or 8 by 16 pixels. There's a 256 byte table that explains where the sprites should go, and it sets their X and Y and their tile index. So for each sprite I can independently move a little 8 by 8 slice of a tile, and I can place it anywhere on the screen I like. It can only be one of the first 256 tiles because we've only got 1 byte to store the tile index, and there's no space to store palette index 2. So all of the sprites, there's no space to store something to allow me to choose the palette, so all of the sprites use the second palette. There's actually a 64 byte hole in the sprite table here that's unused. Presumably at some point the hardware designers thought that they were going to use X, Y, tile index and maybe some attributes, but they never did. So that 4th byte of the 64 sprites in the 256 byte table is spare, and I've noticed some games packing extra tiles in that area, as the sprite table is essentially in the middle of the tile RAM. So here is that same scene we were looking at before, except that now we can see Wonder Boy and some gold coins above him and one of the little snake things that's about to attack him. Let's look at how that looks. Here is the sprite table, and we've got the 64 from 0 to 63 entries in the sprite table, and you can see that we have X, Y, and then tile number. And what that corresponds to, for example, is that first 6 set of tiles there corresponds to the 6 sprites that actually make up what we would think of as a sprite. You know, you think of Wonder Boy himself as being a sprite, but from a hardware perspective, he's made up of 6 sprites all put next to each other. So that's Wonder Boy. The next 4 here make up the little snake dude. These 2 over here are the coin that's flipping around. And then this Y position, this magic Y position of 208, was a marker to say, stop rendering sprites. That's the last entry in the table. So whatever the hardware was doing is it started at the 0th entry in the table, and it ran through until it hit this Y position, which said there's nothing more. So even though you can see in 13 and 14 there is some valid data here, and then from 15 onwards there's nothing, these are not looked at. These were presumably sprites that were on the screen earlier, but have been since either come away or have been killed or whatever. Certainly there's no need to write zeros into there, so we just write a marker that says that's the end of the sprites right now. The sprites also supported some sort of collision detection. That is, they were transparent. One of the colours, one of the 15 colours one of the 16 colours, was a transparent colour that you could see through. When 2 sprites tried to fight for the same pixel, if they were being drawn over each other, a bit was set that allowed sort of primitive collision detection, but it was very difficult to know which 2 sprites had collided, so I didn't ever see any games using it particularly, but it was there if you wanted it. And then as part of the sort of general fetch of the screen, what I believe is happening is at the beginning of each horizontal line on the screen, the hardware walks that whole sprite table and works out which sprites might be visible on that line. And then it would pick the right slice of each sprite to draw as it was going across. And that process, that intermediate process, only had room to store 8 active sprites. So if there were more than 8 sprites on a single line, anything after the first 8 would be dropped. And that's what's happened in this picture here. So this is that original picture of Altered Beast. We can see we've got 2 flappy wing bat things coming down from the top. The right hand one is fully drawn over here. Where's my mouse pointer? There. Over here. But the left hand one, unfortunately, has overflowed the 8 possible sprites. And so we only see a little bit of it. What games typically did at this point would be they would sort of cycle through the sprites so that they all had an equal opportunity of being in the first 8 at any time. And so you would see the sort of flashing, flickering thing if there were 2 too many sprites on the same line. So not ideal, but I guess a workaround, a decent enough workaround. We're going to very quickly talk about sound, as I realise that I'm talking and time is ticking on. The sound chip was a fairly standard chip used at the time. It had a pretty simple 4-channel output. 3 of them were square wave and 1 was a noise channel. Each channel could be configured to have a volume, and it had 2 bytes of frequency. So there was just a single register you would write to with these different bit patterns to sort of pick what whether you were changing the volume, the high or the low frequency of a particular channel. And so to make an emulation of the sound, effectively what we're doing is we count down the frequency that was set in, the value, the high and low bits that were set in here to pick the frequency. We use to initialize a counter, and then depending on both the sample rate of the web browser that we're outputting to and the actual frequency that we're emulating the sound chip running at, we just tick that counter down. And then every time that counter goes below 0, we restore it to its original value, or add on the original value to sort of put it back up to start counting down again, and we toggle whether we're outputting a 1 or a 0. That gives us a square wave with a period of this frequency that was selected. And then we sum up for all the channels where either a 1 or a -1, depending on when we're on, times the volume. And that just gives us an attenuated square wave running at the correct frequency. So there was also a noise channel. That noise channel is effectively a white noise, or ish. If you look at how the noise functions worked, it was a linear feedback shift register, which is a poor man's random number generator. As you can see here, if you've ever written your own random number generator, it looks something like this, where you're sort of shifting bits around. So you start with a value, and then each time you call this, you shift things around, exclusive OR it with itself, and then you return whether or not the bottom bit is set, and that gives us a 1-bit output that is going to oscillate between 0 and 1. Now, this does have a period. It does actually repeat after a relatively short amount of time. So although it was a noise sounding, sort of a white noise sounding thing, it had some kind of period to it, which could be exploited to make other effects. So we put it all together, and we end up with this. Well, this is a screenshot of Teddy Boy, which was at one stage my favourite game on the Master System after the disappointment of Altered Beast. And hopefully, if I have this still up, what I have now over here is Wonder Boy 3. And in fact, I've caught it not through design, but almost in exactly the same pose as it was before when I showed the sprites. So here is the web page that I have it running at. And one of the things, if you're writing an emulator, one of the things that's really, really worth investing time in is writing an integrated debugger. So over here we have a full debugger going on, and I can set breakpoints and I can single step and all that kind of stuff. But I am just going to continue playing this, and you can see it's running the demo actually at the moment. And there is Wonder Boy running around doing his thing, and that's it really. I mean, there it is, running in JavaScript in a browser. Runs pretty well on phones nowadays. It's pretty impressive how fast browsers have gotten these days. So I'm going to stop that again and go back to the presentation. Just a quick word on optimization. If you're interested in this kind of thing, I would recommend actually looking at my BBC Micro talk. The emulator for that is a lot more sophisticated. I've spent a lot more time on it, and I've spent a lot more time looking at optimizing it and making it go fast. Measure first is just a key thing. I have to say that I'm sort of almost contractually obliged to say measure first. Optimization is one of the most fun things to do. It's really challenging, it's interesting, but it's only worth doing if you can show that it was necessary and that your optimization really did make things go faster. So measure first, measure second, measure afterwards. And then table lookups are the key. Anything that you can pre-compute, you put in a table. Even today, with processors being as fast as they are and RAM being as slow relatively, it was worth making tables for a lot of things. So certainly inside the video unit, there's a lot of tables. You saw how the Z80 processor has tables for all of its intermediate flag setting things. That was definitely a worthwhile thing to do. Browsers nowadays support typed arrays, and moving to uint8 arrays and uint32 arrays made a giant difference in the performance. Using asm.js type constructs, where you would like pipe with 0 to just prove to the compiler, the JavaScript JIT compiler that is, that this value is never going to be anything funky. It's not going to be a nan, it's not going to be a string, it's going to be a number. That pipe 0, the result of that is defined to be an integer number. It's not a double or anything like that. That seems to help a little. I don't know how true that is nowadays, but so definitely worth going back and measuring that, I should say. Making things constant helped, at least back when this talk was originally written. Nowadays, I think, again, the JITs are clever enough to notice that a value is not modified and can assume that it has not changed, and then fall back if it does change later on. But obviously, the more hints you can give the JIT compiler, the better. So that's everything I've got to say right now about the master system and how you would emulate it and how you'd emulate it in JavaScript. My details are on there, the screen right now. I'll put them in the show notes, the video notes. It's open source, so go take a look at the source and have a laugh at it. You can play it at the link there. The Xania org is a link to it. Oh, and thank you, YouTube. There is a lot of information at smspower.org, and Richard Watkins, my partner in crime in the original Miracle, or rather the progenitor of the original one, I should say, has written a lot of documentation there, which has helped a lot of people understand how to emulate a Sega Master System a lot better, including the guys from LizardCube, who have made the most amazing version of Wonder Boy 3. You must go out and buy it immediately. It's on Wii, it's on Steam, it's on the Nintendo Switch. Just go get it. It's wonderful. It's a beautiful version of it. It shows the original game off to its finest, and it also shows how you can take the original game and make it look absolutely beautiful by giving it modern graphics and a live soundtrack. So do check that out at lizardcube.com. If you have any questions, don't hesitate to email me. If you've liked this video, please comment or like, and don't forget to subscribe. I will be doing some more videos both on this, on other emulation, on other low-level stuff, and maybe some C++ stuff in the future. Thanks.